So I'm going to present to you a work in QCD pressure, finite temperature, and high magnetic fields. We are using actually perturbative QCD to do the calculation. And this work is in collaboration with Professor Eduardo Fraga from Rio de Janeiro Federal University and with Leticia Paliares from Rio de Janeiro State University. Okay, so let me show a little bit the outline. So first I'm going to give a brief motivation for the work. Then I'm going to talk a little bit about the quark pressure at high magnetic field. Then I'm going to talk a little bit about the QCD coupling constant and the different ways of she runs with a magnetic field. Then I'm going to show some results and then a few conclusions. So there are some places where you can find strongly interacting matter at high magnetic fields. So you can find it in heavy ion collisions where you have the square root of EV about 100 mies. And in magnetars, you have this value of the magnetic field. And of course, in the early universe, you have magnetic field a few orders of magnitude higher than in heavy ion collisions. So from the theoretical point of view, there is an increasing interest in searching for the critical temperature at which strongly interacting matter have changed from free quarks to hadrons, right? So the phase, this is the phase diagram. For here you have temperature and magnetic field. So in this work of Androdi in 2015, he found then the critical temperature up to 3.45. I don't remember exactly. And in of this regime, actually you have a crossover, a real transition. And more recently, this year actually, Delia and collaborators, calculate this critical temperature for two values of the magnetic field, for 4 GeV square and 9 GeV square. And they found that at this magnetic field, you have a crossover, and at this magnetic field, you have a first order transition. So between these two values of magnetic field, you are going to find a critical point. So this is what they are looking next, find the place of the magnetic field value where you are going to find that critical point. So motivated on these works, we wanted to know how perturbative QCD, what are the pressure given by perturbative QCD at this extremely high magnetic field. So let me speak a little bit about the quantities we are using. We are calculating the quark pressure at finite magnetic field. So we are going up to 2 loops. So we have here the 1 loop pressure that is commonly called the free pressure. And this is commonly called also the exchange diagram. So first let me talk about the free one. So we can write it in this way when you have here a pure magnetic contribution, similar to one that the others show in the morning. And you have here the thermomagnetic contribution, right? So you have here assumed in Landau levels. And of course, there is the discussion about this term, right? There is not the only way you can write this expression. There are other forms that consider non-massive term, right? And you can find, for example, another normalization scheme in this work here. And there is a recent discussion in the context of effective models in this work here. But if you are at very high magnetic fields, you can use the lowest Landau level approximation. This is valid for the mass of the quarks much lower than the temperature square and much lower than the magnetic field. So when you do this approximation, so the free quark pressure, the lowest lambda level is this one here. And in this work of 2013, Blesseau, Fraga, and Palhares calculate in this approximation this expression for the exchange diagram. So something I want to say is that, in fact, these integrals here, these momentum integrals, are very, very numerically involved. So you have to be careful to have the right answer. It's not straightforward to do these integrals. So I'm showing here the result they got. The principal result is that they are showing here the exchange pressure as a function of the mass of the quarks. And what they found is that actually the exchange pressure increases with the mass and also increases with the magnetic field. So this is the lower magnetic field. This is 100 times the mass of the pion square, and so on. So it increases with both, with magnetic field and with the mass of the quarks. And here they are comparing how much the exchange diagrams compared with the free quark. And you can see here that is quite small. So we wanted to calculate the pressure for a big range of temperatures and a big range of magnetic fields. So in this expression, actually you take a lot of time because this, as I said, this integral is numerically involved. So we're thinking if there is maybe a better way, numerically speaking, to calculate this expression. So the answer was quite simple. Instead of doing what is done normally, that you first calculate the mass of frequencies, and then you calculate the integral like here. This is given by calculating the mass of frequency. You get all this long expression, and then you integrate numerically in the momentum. You can do the opposite. First, integrate momentum, and then numerically calculate the sums. You have to be careful to sum enough mass of frequency, right? But this expression is quite simple. Quite simple, and these factors here are basically energies that depends on the mass of frequencies. But you have a price to pay. This expression is only valid for zero chemical potentials. The other one is valid for temperature, finite magnetic field, and finite chemical potential. And by doing this, you lost this possibility. Numerically, yeah, numerically. This is too much faster. It's too much. Another thing that we want to check is what happens when you use different QCD couplings. I mean, there are, as Ricardo and William talked in the morning, there are different ways to explicitly write the coupling constant. So, for instance, Professor Ayala and collaborators calculate the one loop or corrected one loop expression using renormalization group analysis, and they found this expression here, which is explicitly dependent on the magnetic field. But this one I'm writing here is to zero temperature. And there is another one, for instance, this one using the color Coulomb potential. And you also can use an answer like this one. So let me show you the result of this work here. So what they found is that for the coupling constant depending explicitly on magnetic field and temperature, they have this behavior here. This is magnetic field, and this is the coupling. So if EB is greater than T squared, they found that the coupling increases with the magnetic field. Same for the case of T equals 0. The coupling constant increases as the magnetic field increases. And in the case of the magnetic field less than t squared, the coupling constant decreases. All these were motivated to reproduce inverse magnetic catalysis, right? So what we are going to do then, we choose 5 different ways of calculating the pressure. So this is the first, the blue one, is to affix coupling. Then in this one, we are using the magnetic field dependent coupling, this one here, right? But with a constant scale. And in this green one, we change the scale by 2pt, what is commonly used in thermal QCD. And we use, again, the explicitly dependent coupling constant. The red one, we use the usual way, only we change the scale by 2pt, runs with t, but is independent of magnetic field. And this last one, we use an answer. So the scale of the coupling constant depends via the scale by changing the temperature and the magnetic field at the same time. So these plots here allowed me to know where my approximation is valid, right? I use in perturbation theory, so my coupling constant cannot be cannot be too large, right? So one has to be careful at which temperature you are calculating the pressure, right? So we see here that these two ones, right, are, of course, very high at lower temperature. This is the one that the scale depends on temperature, so a lower temperature is going to increase. Here is for 9 GeV square, and here for magnetic field 2 GeV square. So here, of course, you have more restriction, right? You can use perturbation theory like above 300 MeV, right? And here I'm showing for a constant temperature and changing the magnetic field, right? So as expected, these ones that depend explicitly on the magnetic field increase with the magnetic field. And at some point, so for a larger magnetic field, the perturbation theory is not valid anymore. So here I also show you the mass of the strange quarks. It changes similar to the coupling, right? Increases here at the temperature, decreases. And here in black, I show you the line that is the mass of the strange quark equal to temperature. So in this region here, the lower lambda level approximation is not valid anymore. So I have also to take this into account to know if my approximation is valid, right? Okay, so this is the pressure, showing these two plots here. It is the only to the strange quark. This is only the strange quark contribution. Here's the free pressure, only the free part. Here is the exchange pressure. This is the comparison between the exchange pressure and the free one. And this is the total pressure. So we can see here that for this magnetic field 2 GeV square, you don't have in the free pressure, at least, you don't have a difference, or at least too much difference between the results. And also in the total pressure, you see that the data is almost the same for all the choices. For the exchange pressure, we have this behavior. The exchange pressure decreases with temperature until it gets the minimum, and then increases again and going to zero. And we can see the comparison. It is effectively quite small, and you can see that between these two, there is not too much difference to tell. When I increase the magnetic field, then I start to see difference between the choices. Of course, these choices here that are dependent on the magnetic field. As they increase with magnetic field, at this high magnetic field, you are going to find difference between the data. And something important to show you here is that this point in particular here. So the exchange pressure is given 0 at the same temperature for all the choices. So it is independent of coupling constant, and it is independent of the mass. What is moving? And OK, here I show the comparison between the two. And we see that for temperature higher than 400 MeV, the comparison is almost 0. And let me show you then this plot here when I show this line divides the region where the exchange pressure is positive with the region where the exchange pressure is negative. So if you choose magnetic field and increase the temperature, there is going to be a temperature where it becomes 0, and then if you continue increasing the temperature, it changes sign. And finally, I show the pressure with depending on the magnetic field for a fixed temperature. So as we already tell from the plot before, for higher magnetic fields, the results are going to deviate. And here for the exchange pressure, as also expected, the couplings that we choose that depend explicitly on the magnetic field, the ones that increase with the magnetic field, are going to give a greater contribution for high magnetic fields. Here I showed for a much higher temperature. So in this case, the thermal part dominates, and you don't see a very big change between the choices. And the exchange pressure in this region is, at least for these magnetic field values, is always negative. So these are the conclusions that I have. So in general, we found the same qualitative behavior. So for all alphas chosen, the contribution of the exchange pressure is quite small compared to the free pressure, with the exception of extremely high magnetic fields. And the different renormalization schemes and their impact in the pressure should be further studied in the context of perturbative QCD. And of course, it would be great to have QCD pressure data for high magnetic fields in the near future. So thank you.
Tulio, when you can start to trust in lowest lambda level approximation, which value of P you can trust? From this value, I can trust in this approximation.
OK, one thing you can do is, of course, do it numerically. You can calculate the first Landau level, n equals 0, and see the other one, and see if it is, I don't know, 4 or 5 orders of magnitude less than the other one. But you have to, this have to be always truth, right? So you must be sure that your mass is lesser than the temperature. It's too much lesser, but too much lesser is, I don't know how much, right? And lesser than in the temperature has to be temperature square, lesser than the magnetic field. So you cannot have a magnetic field that is lesser than the temperature square, for example. That region is not allowed for the approximation.
In a second question, please, is the exchange pressure seems to be negligible if you compare with the free one always in orders of.
Yeah, it's quite small.
When you have the total pressure, is the free.
You can see it here, for example. Yeah.
Yeah, if you look
in
at
this case, you don't see too much. Here you see a little change here for lower. And if you go too high, I have one. Let's do here. This is absurd magnetic field, right? But I just wanted to see one. And now you see it changes, right? This is not exactly the same. So you see contribution. For this temperature, you already have the exchange pressure equal to the other one. But of course, this is ridiculous. This is the approximation is not valid here. So.
Thank you for the talk. why are you just considering the strange quark contribution and not the light quarks?
Okay. Actually, I am in the work I'm doing. I'm considering everything, but I wanted to show just this one here because this is the one that depends of more in the running of the mass, right? The others, the changes when you run the scale don't not change too much as the strange quark. So you have changing the mass from more than 100 MeV to very low values of the mass.
Because I would expect that the light quarks are even more sensitive to the magnetic field. They're basically just a factor of 30 between their masses, and
it's because I wanted to
so they feel the magnetic field.
The effect of the running here,
Mm-hmm.
also in the pressure. That is the reason.
Mm-hmm.
But in fact, to the total pressure, I calculate everything.
And another question. So you say that the exchange pressure is always negligible with respect to the free. That seems like the case.
Yeah.
Is this statement independent of how you regularize it, the pressure at zero temperature? In the beginning, you mentioned that there is some ambiguity there.
I didn't taste that, but I believe it should depend, right? Because one renormalization goes to zero when the mass goes to zero. That is this the case here? This one, right? Mass goes to zero, it goes to zero, but it goes to infinity, it goes to infinity, right? And in the other way, like you do, is the contrary, right? Mass goes to zero, this expression explodes, and mass goes to infinity, this expression goes to zero. So it should depend, right?
More questions? No? So let's thank the speaker again.